So slope fields, as you have learned, the solution to a differential equation of the form dy dx is equal to f of x is found by taking the antiderivative and including a plus c, because it can vary by any constant. Meaning that we could just slide the graph up or down, and all of those graphs would have similar slopes. But if they vary by a constant, we would be moving them up or down. So here's the definition that you need to know. A slope field is a series of very small segments representing the slopes of these solution curves at various points throughout the coordinate plane. We can call them little baby slopes. All right. And so I think it's helpful to make a chart when we are working these. Example 1 says create a slope field for dy dx is equal to 1/2 x. So I'm going to make a little chart here. I've got x, I've got y, and I have dy dx. And so what I'm going to do is look at the coordinate values of x and y and plug them here into my equation. There is no y variable in this one. There is in the second example, but in this one, I can ignore the y variable because there is not one in my equation. And so let's start with some of the easy ones. If I plug in 0 for x, I'm plugging 0 into this equation, which gives me 1/2 times 0, which means that dy dx is 0. And it means that I have a slope of 0 at every point where x is 0. Therefore, all up and down the y-axis, I have a little horizontal baby slope of 0. So I need to draw those slopes so that it looks something like that. And so now I'm going to pick another point. Let's say that x is 1. If x is 1, then my slope, dy dx, is going to be 1/2. And so all up and down the vertical axis where x is equal to 1, I need a slope 1/2. So this is where I think it's helpful to use your ruler. Let's start at this dot right here. And to draw a slope of 1/2, I'm going to go up 1 and over 2. So line it up with this dot. And let's draw a little baby slope of 1/2. And then I'm going to slide my ruler up to the next dot. I go up 1 and over 2. And that one's going to be parallel. And I'm lining up this dot with this dot so that it looks like that. And it looks like that.
Exact.
Stop.
Baby slopes.
And if x is equal to -1, I have a slope of -1/2, which means on the left side here at x is equal to -1, I have slopes of -1/2. So I'm going to do the same thing, but my slopes will be negative. So for example, starting at this dot, I go up 1 and back 2, line it up with that dot, and draw your slopes so that they should look something like that. And they don't have to be a calculus work of art like mine, but they need to be close.
What's the ruler for? Is it for like?
The ruler is just to draw the little slopes if you want to line up the dots. Okay, so if x is 2, then I'm going to have a slope of 1. And so if I go out to where x is 2, I would line up the dot that is up 1 and over 1. So that one obviously is going to be a little bit steeper than the last one that had a slope of 1/2. And if x is -2, I will have a slope of -1. So I'm going to go over to the other side. And draw in those slopes. And the last two here, if I plug in 3 for x, I get a slope of 3/2. And so again, I can start at this top dot and go down 3 and back 2. So 1, 2, 3, and back 2. I'm lining it up with this dot and drawing a slope of 1.5. And then these are all going to be parallel, but I can line it up 1, 2, 3, and back 2. It's a little bit steeper than the last one.
It seems like it'd be hard to grade.
I will explain in just a second how they grade it. Okay. And if it is -3, I'm going to have a slope of -3/2. Okay, so down 3, 1, 2, 3, and over 2. So that it looks something like that. And so let me show you something that I hope will click and help this to make sense. If I have dy dx is equal to 1/2 x and I wanted the original equation, if I have the first derivative, to get back to the first equation, I would need to take the antiderivative. So if I take the antiderivative of 1/2 x dx, the antiderivative of 1/2 x, I add 1 to the exponent and divide. That gives me 1/4 x squared plus my constant. And this is going to be y equals because it is with respect to y. So if my derivative is linear, that means my original equation was quadratic. It had a degree of 2, and a quadratic equation is a parabola. So can you see the parabola in the pattern? Hopefully so, otherwise you did something wrong, right? And that's slope fields. That's all that slope fields are, okay? So we're going to look at one other example here where we are drawing. Example 2 says create a slope field for dy dx is equal to y times x minus 1. And in this case, I have an x variable and a y variable. And so, again, I think that it would be helpful to make a little chart there. But you don't have to necessarily. Okay, so let's do the easy ones first. I'm going to plug in 1 for x because if x is 1, that means my slope has to be 0. Y can be any number. It doesn't matter. I'm multiplying times 0, so my slope is 0. That means if I go out to where x is 1, on this vertical axis, I'm going to have little horizontal baby slopes of 0 at every point. And another easy one, if y is 0, that means that dy dx is 0, no matter what x is. It could be any number. And so all along the x-axis where y is 0, I'm going to have horizontal baby slopes of 0. And so now this could be a little tedious, but this is the only problem that we have to do this on. what we have to do now is look at the coordinate points for each of the dots and draw the slope. So let's look at, let's look at this one, for example. At this coordinate point, I go over 2 and up 1. So x is 2 and y is 1. And if I take those and plug them into my equation, I get 2 minus 1 times 1, which is 1 times 1. So my slope is 1. Therefore, I'm going to make a little mark there that has a slope, a little baby slope of 1. And then if I go to the next coordinate point above that, x is 2 and y is 2. And if I plug in those values into the equation, I should get 2 times 1, so that my slope dy dx is equal to 2. Down 2 and back 1. It's going to be a little steeper. It should look something like that. And so let's do the ones below that there. I'm going to plug in 2, -1. And when I do that, x is 2 and y is -1. So I'm going to have a slope of -1. And then the coordinate point below that would be 2, -2. And that's going to give me a dy dx of -2. Oh, wrong button. Okay, so what I need you to do right now is fill in the rest of the coordinate points, please. And but first, let me explain how. Well, as you're doing that, I will explain how most likely they will grade this on the AP exam. So if you get a slope fields question, that's a free response. It's probably worth 2, possibly 3 points. So 1 point would most likely be the horizontal slopes. So they would look to make sure that you got all of the horizontal slopes right. And then the other point would be for everything else. And so as long as you have the correct sign, the negative slopes, excuse me, the negative slopes are negative and the positive slopes are positive and everything looks close, you should get credit for that. Okay. It's not like they're going to look at one exact coordinate point and see if you really got a slope of 3/2, for example. If it's close, they're going to give you credit. All right, so I'm going to continue my little chart here.
For the negatives, you think we could just like just do the same thing? You know what I mean?
I don't. What do you mean?
Because like they're parallel, kind of.
Like
they're matching.
Like a reflection.
Yeah.
Right. I think that's okay.
Does it matter what side of the point our line is on?
What do you mean?
Like, I don't understand it. Do they all have to come from like this side of the point or like joining them?
I don't think that matters what they're looking at. Okay, if I were grading this, I would look to make sure that I got the horizontal slopes correct.
Okay.
And then I'm going to check and make sure that, for example, all of these in the first quadrant have to be positive. And these in the fourth quadrant here have to be negative. And one is going to be steeper than the other, right? And so I would just grade it like that. So 3. -2 is going to give me a slope of -4. Make sure you do the y-axis also. Don't forget those. So again, can compare yours to mine here. And like I said, it needs to be close, right? If we were doing this on the AP exam, number one, you probably wouldn't have as many dots to fill in. You might have 10 or 12, something like that. They're going to check the horizontal slopes, make sure those are correct at 1, at x is equal to 1, and then along the x-axis. And then they would probably check to make sure the sign is right in each quadrant and that they are reasonable there. And that is slope fields, okay? There's one other thing that you probably need to know how to do, something associated with slope fields. And that is if they give us a slope field, given the slope field shown for the differential equation dy dx is equal to x plus y, we need to sketch a graph of the particular solution. And so the way that we do that is we are going to sketch a graph that follows the slope field, and it also has to go through this point 2, 0. So for example, if we were doing this on the first one, and they asked us to sketch a particular solution, we would need to draw a parabola that follows the slope fields of the first one here. So on this one, the first thing I would do is graph the points. So 2, 0 is going to be right there. And my graph is going to have to go through that point, and then it will need to follow the slope field. So you can see the slope field kind of angles up to the left, and over here kind of curves and goes upward. So I'm going to sketch a graph that follows that. And again, it's got to go through the point, and it's got to reasonably follow the slope field. So it will look something like this. Any questions on any of the first 3 examples there on the first page? Well, let's take a look at the second. And here, they give us 4 sets of differential equations and 4 slope fields and ask us to match them. All right, so let's work a little example like that. On the first one here, I have the derivative is equal to x. So my derivative is linear, meaning that the original equation was a parabola. All right, and so I'm going to look for the sketch of a parabola in my slope field. And so it has to be the second one B here. And then I would probably go to the trig function. My derivative is sine of x. So my original equation was negative cosine of x. And so which one of the slope fields looks like a cosine graph?
The last one.
It is indeed the last one. And so for the other two, what you need to do is to pick test points and check them out. For example, let's say that I look at the second one. If y is 2, then my slope would have to be 0. So I need to have horizontal slopes around where y is 2. And that does not work for the first one. But here on the second one, it does work. So this one has to be the second one. And the last one is going to be the first one, but I will pick a test point to show you how it works. Again, let's say that I choose 1, 1 for x and y. Therefore, I should have a horizontal slope of 0 at the coordinate point 1, 1. And you can see that works for the first one here, because at this coordinate point 1, 1, I have a horizontal slope of 0. Okay, so look at the next one and see if you can match up the 4 differential equations with the slope field. Take like 2 minutes to do that, and then we will check them.
There's a circle in here, bro. What? Hmm. Oh, I was wrong.
And why don't you check with your neighbor there to see how he or she is doing?
Hmm. Not racial. That's true.
Yeah, that's what I got.
Look at me, Mr. Nas.
Jacob, what'd you get?
4, 1, 2, 3.
Oh, I switched 1 and 4.
I don't know, you probably.
Yeah, you're
I
stupid.
don't know.
Okay, man.
I'm sorry. I'm sure you're a smart man, but
Here we go, let's look at this.
One day.
So if I were working these, I would probably start with the parabola. There's a parabola in D there, which means it has to be this one, okay, because I have a linear function, y is equal to 1/2 x, so this one has to be 3. And then for the others, we're going to pick test points. So for example, on the second one, if y is 0, I am going to have a slope of 0. So it needs to have a horizontal slope field as it approaches the x-axis, okay? And the one that fits that is this one, C. Or for example, number 4, if you will notice, if x and y are positive, if x is 1, 1, or excuse me, if x and y are 1 and 1, or 2 and 2, or 3 and 3, then my slope has to be negative. So everything in the first quadrant has to have a negative slope. And that does not work for B, but it does work for A. So this one has to be number 4. And B, if you can pick a test point there, let's say 1 and -1, for example, it's got a horizontal slope. 1 minus 1 would give me a slope of 0, and that works for this one. So it should be 4, 1, 2, 3 there.
It's the same answer, Mr. Newhouse.
That's what you got?
No, it's the one above it. So uncreative. Unoriginal.
Maybe I'm just trying to throw you off so that when you, hey, count the number of A's, count the number of B's, number of C's, and then
Okay,
take a
but-
wild
Okay,
guess.
but you're never gonna do 4 A's in a row.
All right. Never know.
I will change that if you put 4 in a row.
All right. So last thing that we're doing here, solving differential equations, initial value problems. If you go on to do higher math, you have a whole course on differential equations, right? It's like Calc 4, Calc 1, Calc 2, Calc 3, and then differential equations. Here, whenever it says solve the initial value problem, that means we are going to solve the equation for y or another variable, the original equation. So on these problems, for example, they're going to give me a derivative, dy dx, and then say solve the initial value problem, which means I need to have the original equation, y is equal to whatever that is. So since they give me dy dx, which is the first derivative, and I need to get back to the original equation, I'm going to take the antiderivative of dy dx. So I'm going to have the antiderivative of sine of 2x dx. So what is the antiderivative of sine of 2x?
1/2 cosine. Oh, shoot.
So it's -1/2 cosine of,
2x.
keep going, plus my constant. Okay, and I know that this is equal to y. How do I know it's equal to y? Because it's dy dx. And it's Monday, and I'm a little slow. Can you go back and explain how you got the -1/2 cosine of 2x? But wait, so I think what you're saying is like the antiderivative of sine of x is negative cosine. And the 2x stays the same. And then since I'm taking the antiderivative, I've got to divide that 2 into the coefficient, which is where the 1/2 comes from.
Mhm.
Okay. So now, in order to solve the initial value problem, I need to write the equation, and I am missing a variable, which is c, but they give me some more information here. They tell me that y is equal to 3 when x is equal to pi over 4. So that's going to give me 2 times pi over 4. Trig values again. What is the cosine of pi over 2?
She's right.
We're positive. I will agree with that. It is 0, which means that that goes away. And that c is equal to 3. That implies that c equals 3. So now I'm going to write my original equation. I have y equals -1/2 cosine of 2x plus 3. And so this is the original equation that meets all the criteria that they gave me. When I take the derivative, I'm going to get sine of 2x when y is 3 and x is pi over 4. That's it. That's all they're asking you to do on this. On the next one, however, they give me the second derivative, which means I'm going to use the same process, but do it 2 times, okay? So if I take the antiderivative of this, first of all, what is my variable? It is u. And so if I take the antiderivative of the second derivative, I'm going to get the first derivative, which is du dx. And the antiderivative of 12x is 6x squared. I think you said a plus c, right? But I'm not sure I heard it there. So it's 6x squared plus c, right? All right, so now I need to solve for c, and here they tell me that du dx is 5. And they also tell me that x is 2. And so solving for c, I have 5 equals 24 plus c, and that means that c is negative 19. Solving for c. So now I can say that du dx equals 6x squared minus 19. And I'm solving for the initial value, which means I need to get back to the original equation. So I'm going to repeat the process again. So the antiderivative of du dx will give me, hold on, the variable will be u, right? Because it's with respect to u. And the antiderivative of 6x squared is 2x to the third minus 19x plus c. And now I'm going to plug in the value for u and the value for x. So u is 3 when x is 2. So I plug in 2, and that gives me 2 times 8, which is 16 minus 38 plus c. So that gives me 3 minus 3 equals negative 22 plus c. So c is therefore 25. And so now I can write my original equation. I have u equals 2x to the third minus 19x plus 25. Cry me a river. Just wait till we get till tomorrow. All right, I got one more here.
Won't do it.
You're welcome to abstain from doing your work. However, you shall face the wrath of the supreme calculus dictator. Here we go. The concavity of y, f of x, is found using the expression 12x. The function has a slope of 5 at the point 2, 3. What is f of x? So they are asking for the original equation. And this time they tell me the concavity is 12x. So writing that in terms of the derivative, concavity is the second derivative. So I'm going to write this as y double prime. Does that look like a double prime there? Kind of.
Nah, one prime.
Now we're in business. So I'm going to take the antiderivative. When I take the antiderivative of y double prime, I get y prime. And here I get 6x squared plus c. And I know that y prime is what?
5.
How do you know this? It says the slope is 5 and x is 2. And I know that c is negative 19 and y is 3. And so I realize that this is the exact same problem. However, same as 6b, but here's the difference, but with different notation.
Still on an original making these notes, doesn't it?
Why have to make that example 6b or
Well, what I want you to see here is that
It's perfect.
they give you the concavity and they give you the slope, which is the same information that they gave you in the previous problem, but the notation is different. Okay. So that is slope fields and initial value problems.
Yeah, I'm done.